Hello everyone. So before starting the video, first and foremost I would like to thank the Department of Physics, Dr. CP Sir, Namchi Government College and the Sikkim University for providing me such a beautiful platform to make a video for the partial fulfillment of BSc Honours 6th Sem 2021. Hi, this is me Madhav Gurung, bearing roll number 18NS0011, and this video carries 25 marks instead of 25 marks practical examination. So now, today in this video we are going to learn about the introduction, principle, construction, working and the limitations of a cyclotron. Cyclotron Cyclotron is a device used to accelerate charged particles to high energies, and it was devised by Lorentz. So basically, cyclotrons are used to accelerate heavy charged particles, okay, like protons, deuteriums, and heavier ions. And the cyclotron was invented by, like I said, Ernest Lorentz in the year 1930 as a tool for physics research and isotope productions. So this was a brief introductions about cyclotron. Now let's move on to its principle. Cyclotron works on the principle that a charged particle moving normal to a magnetic field experiences magnetic Lorentz force, due to which the particle moves in a circular path. So basically it works on the principle that whenever a charged particle is moving normal to a magnetic field, at that instant of time the particle will suffer a magnetic Lorentz force. Okay, it will experience a magnetic Lorentz force, as a result of which, as a consequence of which, the particle moves in a circular path. So now here you all can see in the figure there is the constructions of a cyclotron. So now it consists of a hollow metal cylinder divided into two sections, D1 and D2, called Ds, enclosed in an evacuated chamber, like shown in the above figure. You all can see there. The Ds are kept separated and a source of ion is placed at the center in the gap between the Ds. So please don't get confused, okay? So by the term a source of ion, it may be anything, it may be a charge, so which is placed at the center in the gap between the Ds. They are placed between the pole pieces of a strong electromagnet. The magnetic field acts perpendicular to the plane of the Ds, and the Ds are connected to a high frequency oscillator. Like in the figure, the oscillator is like represented by, as you all can see, D1 and D2, which is connected to a high frequency oscillator. Now let's move on to the working of the cyclotron. So when a positive ion of charge Q having mass m is emitted from the source, it is accelerated towards the D having a negative potential at that instant of time due to the normal magnetic field. As I already mentioned, the ion experiences magnetic Lorentz force and moves in a circular path. By the time the ion arrives at the gap between the Ds, the polarity of the Ds get reversed, and hence the particle is once again accelerated and moves into the other D with a greater velocity along a circle of greater radius. Thus, the particle moves in a spiral path of increasing radius, and when it comes near the edge, it is taken out with the help of a deflector plate dp. You can see deflector plate in the diagram of or in the constructions of the cyclotron. Okay, the particle with high energy is now allowed to hit the target T. Now, when the particle moves along a circle of radius say r with a velocity say v, the magnetic Lorentz force provides the necessary centripetal force. Here you can see VQV is equal to Vm square by r. Okay, so where VQV represents the magnetic Lorentz force and Vm square by r represents the necessary centripetal force. Okay, and Q is the charged particle which is moving with the velocity v through a magnetic field B. So on just solving the equations by simple cross multiplications, we will get V upon R is equal to BQ upon M, which is actually a constant. Okay, so now let's make this equation as equation number 1. So now we know the basic formula or basic relations to find the time, okay, which is simply given by distance upon speed. So using that basic formula, we can find the time taken to describe a semicircle, which is equal to pi r by v, where pi r is the distance and v is the speed. Now let's make this equation as equation number 2. Now substituting the value of equation number 1 in equation number 2 respectively, we will get T is equal to pi m by bq. Now let's make this equation as equation number 3. So till now it is clear from equation number 3 that we have just got that the time taken by the ion to describe a semicircle is independent of the radius r of the path and the velocity v of the particle. Since all of the mentioned parameters are absent from the equation number 3, on the basis of which we can say that the time taken by the ion to describe a semicircle is independent of the radius r of the path and the velocity v of the particle. Hence, the period of rotation t, which is equal to twice of t. Okay, this can be actually termed as the total period. Okay, so it is given by like t is equal to t 2, and just substituting the value of t that we have just calculated in the equation number 3, we will get the equation number 4 as t is equal to 2 pi m by bq, which is also a constant. Okay, so in a uniform magnetic field, the ion traverses all the circles in exactly the same time. Therefore, the frequency of rotation of the particle is given by nu is equal to 1 upon t. This is the formula for frequency. Okay, like the numbers of oscillation for unit time, v is equal to 1 by t. Now just substituting the value of t from the equation number 4, we will get nu is equal to vq upon 2 pi m, and let's make this equation as equation number 5. So now if the higher frequency oscillator is adjusted to produce oscillations of frequency as given in equation number 5, resonance occurs. Okay, so now as we already have discussed in our introductory part, that cyclotron is used to accelerate like heavy particles, okay, for example protons, neutrons and alpha particles. Now you can see here VQV, okay, which represents the magnetic Lorentz force is equal to the centripetal force, okay, which is given by mv square by r, where r is the radius of the circular path followed by the particle. Now on simple cross multiplications and rearranging the term on both the sides, we will get v upon r is equal to bq by m, which is actually a constant, okay. So let's make this equation as equation number 1. Now we know the time taken, okay, the time taken is given by pi r by v, okay. Now pi r is the distance and v is the speed. So simply putting the value of like v by r, okay, v by r, which we have got in equation number 1, but here it is just in the reciprocal form, okay, like r by v in the equation number 2. So on behalf of that, just simply putting the value from the equation number 1 of r by v in equation number like 2, we will get t is equal to pi m by vq, okay. Now the total period, okay, is given by capital letter T is equal to twice of small letter t. So we have just calculated the small letter t as pi m by vq in equation number 3. So let's find out the total period, okay, and it is given by capital letter T is equal to twice of small letter t, and just substituting the value of small letter t from the equation number 3, we will get the total period as t is equal to twice of pi m by vq, which is again a constant, okay. And let's make this equation as equation number 4. Now in the equation number 4, we have just calculated the value for the total period, okay, of oscillation. Now we can also find the frequency by using that equation 4 in the equation of frequency, which is given by nu is equal to 1 upon t, since frequency is numbers of oscillation per unit time. So now on just simply substituting the value of t from equation number 4 in the equation nu is equal to 1 upon t, we will get frequency nu as vq upon 2 by m. So this is the equation, or you can say the expression for frequency, which is equal to bq upon twice of pi m. So till now we have discussed about cyclotron, like what is a cyclotron, what is cyclotron used for, its construction, principle and working too. Now we will discuss about the limitations of a cyclotron. So at number 1, maintaining a uniform magnetic field over a large area of the disk is difficult, okay. So in the principle we have already discussed that the whole setup is based on the uniform magnetic field, okay. So but in the practical life, like maintaining a uniform magnetic field over a large area for a long period of time, it's quite difficult, okay. So this is the first limitation. And second, at high velocities, relativistic variations of mass of the particle upsets the resonance condition. So now due to the high velocities, there may occur the variations in the relativistic mass of the particle, okay, and due to which the resonance conditions might not occur. So this is the limitations of the cyclotron. And at number 3, at the high frequencies, relativistic variations of mass of the electron is appreciable, and hence electrons cannot be accelerated by the cyclotron. So at high frequencies, the variations in the relativistic mass of electron can be seen, okay, and as a result of which the electron cannot be accelerated by cyclotron. So this much for today, and thank you so much for watching.